Continuing with section 3.5, rational functions and their graphs. Today we're going to talk about horizontal asymptotes of rational functions. I'm not sure where figure, that might be the figure below. Shows the graph of the reciprocal, the graph of the reciprocal function, 1 over x. Of course, you know that should look a little something like this. We are stuck in the first quadrant and the third quadrant. Shows the graph there. As x approaches infinity and x approaches negative infinity, the function values are approaching 0. So the line y equals 0, or the x-axis, is a horizontal asymptote of the graph. Many, but not all, rational functions have horizontal asymptotes. So here's our official book definition of a horizontal asymptote. The line y equals some number b is a horizontal asymptote of the graph of the function f if f of x approaches b as x increases or decreases without bound. So here in this graph, as x heads for infinity, the function is approaching b. Notice it's coming up from underneath it, and it's going to approach but never touch or cross the horizontal asymptote. Or you might have something like this: as x approaches infinity, f of x approaches b. We're now above it and coming down toward the asymptote, y equals some number b. Or you could have something like this: as x goes to infinity, f of x also approaches b. This type of asymptote you can cross. Notice here, as we're going left to right, we cross the asymptote, dip down here, and then we're going to start heading back up toward it, approaching it, but now we're not going to cross it again. Vertical asymptotes you can never touch or cross. That's like dividing by 0. Horizontal asymptotes are just values you approach in the long run. As x heads for positive or negative infinity, it is possible to cross a horizontal asymptote. So recall that a rational function may have several vertical asymptotes. By contrast, it can have at most one horizontal asymptote. Although a graph can never intersect a vertical asymptote, it may cross its horizontal asymptote. If the graph of a rational function has a horizontal asymptote, it can be located using the following theorem. So let f of x be a rational function given by this. Notice we have our leading coefficient a to the n. This is x to the nth power, and then it goes downhill from there. Right below that, our denominator, we have b sub m is our leading coefficient, x to the power m, x to the mth power. The degree of the numerator is n, the degree of the denominator is m. So that is our leading power of x. X to the nth power, x to the mth power in the denominator. If n is less than m, or if the numerator is of a lesser power, the x-axis, or y equals 0, is your horizontal asymptote. If the powers are the same, if n and m are both equal, then the line y equals a sub n over b sub m is the horizontal asymptote of the graph. Notice that is just the leading coefficients. A sub n is your numerator leading coefficient, b sub m is the denominator. You just make them into a fraction. That is your horizontal asymptote. Our last case scenario, if n is greater than m, if the numerator's power of x is more powerful, then you have no horizontal asymptote. Again, maybe a little confusing there when you see one of these in an applied problem. It's a piece of cake, like right here. Find the horizontal asymptote of this rational function, if it even has one. So for part A, I look at my powers of x. This is x to the first, and then I see down here in the denominator is x squared. Denom is more powerful. Denom is more powerful. And I'm just talking about the exponent, the power of x. So the x-axis is an asymptote. X-axis, or you could think y equals 0. That is your asymptote. Denominator is more powerful. You're just going to head for your x-axis. Part B, it's a tie. If you look at the numerator, it's 4x squared. Denominator is 2x squared. We have a tie in the race, so we just take our leading coefficients and make a fraction. Leading coefficient of the numerator is a 4. Leading coefficient of the denominator is a 2. So there's our y asymptote, our horizontal asymptote. Y equals 4 divided by 2 is 2. There's our horizontal asymptote. Last one, letter C. Notice numerator now is 4x cubed. Denominator is 2x squared. Numerator is more powerful. Numerator more powerful. No horizontal asymptote. The function will grow without bound, either positive or negative infinity. No horizontal asymptote will constrain it. And it looks like we got a great question. Do I have to factor to identify a function's possible horizontal asymptote? No. Unlike identifying possible vertical asymptotes or holes, we do not need to use factoring to determine possible horizontal asymptotes. So here we have 4x over 2x squared plus 1. As we head way off to positive or negative infinity, we are headed for y equals 0. Yeah, so that would be this example 3 part A. That's what the graph of that function looks like. Again, we can cross that asymptote, but as we head to the left or the right, we will approach it again. Here's one where we had the tie race, and we did 4 divided by 2 was 2, so that line y equals 2 is our horizontal asymptote. The last one, now the numerator is more powerful. That will cause the function to grow without bound, either up toward infinity or down toward negative infinity. Okay, now we did a previous section of transforming graphs or picking them up and shifting them. We can also do that with our rational function graphs. Below we see the two rational function graphs. On the left is f of x equals 1 over x. So we're stuck here in the first quadrant and the third quadrant. First quadrant, the positive quadrant, and the third quadrant where both values are negatives. So we have that, and we are origin symmetric. 1 over x squared is the volcano-shaped graph. Because everything's squared, it's going to be positive going up. Negative numbers squared are positive, as are positive numbers squared. And because it is an even exponent, we have even function and y-axis symmetry. Some rational functions can be graphed using transformations, like horizontal shifts, stretch, shrink, or reflect, or vertical shifts of these two common graphs. Okay, on example 4, we're going to take the x squared graph, 1 over x squared, and we're going to move it in 2 ways. Now inside here, this x squared, we change that to x minus 2 quantity squared. That is going to be a shift left or right, just like when we were shifting the squared function. So this minus 2 is a shift left or right. If it's minus, we're shifted to the plus side. So we're shifted to the right 2 units. So the asymptote was the y-axis, but that's now been shifted to the right 2 units here. And all points have been shifted 2 units. Notice right off here we have these 2 symmetric points right around our asymptote. So those points are now 3, 1 and 1, 1. And then our graph will look like this. Still have the x-axis as our horizontal asymptote. That's not very good, but you get the idea right there. Okay, now we got this little plus 1 tacked on the end. That's going to take the graph we just made and move it up or down. Since it's plus, since it's plus, this is a shift up 1 unit. So our vertical asymptote is still at 2, but the shift up moved our horizontal asymptote. It's no longer the x-axis, it's now the line y equals 1. And all points also got shifted. So we're still going to have these points. 3, 1 got shifted up a unit, and 1, 1 got shifted up a unit. And now our graph looks like this. Or close, something like that. All right, a few for you to try. Number 3, find the horizontal asymptote if there is one. Number 4, shift that graph. Very similar to the one we just did. Okay, let's see. In the first one, part A, we have a tie, 9x squared, 3x squared, so those sort of cancel. And our horizontal asymptote is the leading coefficients, 9/3, or the line y equals 3. In part B, denominator is more powerful, so our horizontal asymptote is y equals 0, or the x-axis, however you prefer to say it. The last one, our numerator is the more powerful, so it will have no horizontal asymptote. Whoa. Guess I'll just leave those there. Okay, the 1 over x graph is what we see here on the left. If I just do this part first, 1 over x plus 2. The plus 2 is a shift left or right, and it's sort of the counterintuitive one. The plus 2 means we have shifted to the left 2 units. Everything else stays the same, so our x-axis would still be our horizontal asymptote. And we would go through these points and look like so. Now, the minus 1 on the end has shifted that graph down 1 unit. So vertical axis, or asymptote, excuse me, still at -2. Our horizontal asymptote was the x-axis. That's now been moved down a unit. So now y equals -1 is our horizontal asymptote. And notice from this vertex at 1, 1 and -1, -1, just diagonally from that vertex of the asymptotes, we have 2 points. So I can put one of those points here at the -1 on the x-axis, and -3, -2 would be one of those points. And we can draw the graph in there like so. And there we go. Homework, page 406 and 7. These sets of problems. Check the odd ones in the back, of course. See you in class.